On August 14, 2003, at 4:10 p.m. Eastern Daylight Time, the largest blackout in North American history commenced. This event impacted approximately 50 million individuals residing in 8 United States states and 2 Canadian provinces, with power outages lasting up to 2 days in certain regions. The root cause of the blackout was a cascading failure within the power grid. The sequence of events began when a tree branch made contact with a power line located in Ohio, resulting in a short circuit. This short circuit subsequently triggered the power line to trip, leading to a loss of power. This initial loss of power initiated a domino effect, causing the failure of additional power lines and transformers. The cascading failures propagated throughout the power grid, leading to power outages in major metropolitan areas such as New York City, Detroit, and Cleveland. The 2003 blackout presented a significant challenge to the United States power industry and raised concerns regarding the reliability of the nation's power grid. In response to the blackout, both the United States government and the power industry undertook measures to enhance grid reliability. These measures included investments in new infrastructure and the implementation of revised regulations. The blackout had a substantial impact on both the economy and the lives of individuals. Businesses experienced revenue losses amounting to billions of dollars, and many individuals were left without power for extended periods of time. Additionally, the blackout caused widespread disruptions to transportation, communications, and other essential services. The aftermath of the blackout was characterized by public outcry and debates regarding the underlying causes and the necessary steps to prevent future occurrences. Furthermore, the blackout led to a series of investigations and reports, including one conducted by the U.S. Canada Power System Outage Task Force. In summary, the 2003 blackout represented a significant event with far-reaching consequences for both the United States and Canada. The blackout underscored the importance of grid reliability and prompted changes in the operation and regulation of the power grid. Power grids are designed to be resilient, but they are also complex systems that can be vulnerable to cascading failures. A cascading failure is a process in which the failure of one component in a system leads to the failure of other components, and so on, until the entire system collapses. In the case of the 2003 blackout, the initial failure of a power line in Ohio led to the failure of other power lines and transformers, which eventually caused a widespread power outage. Firstly, understanding the grid's architecture is important. The power grid is a network of power plants, transmission lines, and distribution lines that deliver electricity to consumers. Power plants generate electricity, which is then transmitted over high-voltage transmission lines to substations. Substations reduce the voltage of the electricity and distribute it over low-voltage distribution lines to homes and businesses. Secondly, the power grid is designed to be resilient to failures. For example, power plants are equipped with backup generators that can provide power in the event of a primary generator failure. Transmission lines are also designed with redundancy, so that if one line fails, another line can take over its load. Thirdly, despite these precautions, power grids can still be vulnerable to cascading failures. This is because the failure of one component can put stress on other components, which can then fail. For example, if a power line fails, the load that it was carrying will be transferred to other power lines. This can overload those lines and cause them to fail as well. Fourthly, cascading failures can be difficult to predict and control. This is because they can occur very quickly and can spread over a large area. In the case of the 2003 blackout, the cascading failures spread from Ohio to New York City in a matter of hours. Therefore, to prevent cascading failures, power grid operators need to have a good understanding of the grid's architecture and operating conditions. They also need to have the ability to quickly detect and respond to failures. Sixthly, one way to improve the reliability of the power grid is to invest in new infrastructure. This includes building new power plants, transmission lines, and substations. It also includes upgrading existing infrastructure to make it more resilient to failures. Seventhly, another way to improve the reliability of the power grid is to implement new regulations. These regulations can require power grid operators to meet certain performance standards and to have plans in place to respond to failures. 8. The 2003 blackout was a wake-up call for the U.S. power industry. In the wake of the blackout, the industry took steps to improve the reliability of the power grid. These steps have included investing in new infrastructure, implementing new regulations, and improving the training of power grid operators. 9. As a result of these efforts, the reliability of the power grid has improved in recent years. However, the power grid is still a complex system, and there is always a risk of cascading failures. 10. By understanding the causes of the 2003 blackout and taking steps to prevent similar events from happening in the future, we can help to ensure the reliability of our power grid. Electrical grids are vital infrastructures enabling modern society. However, they are complex and susceptible to large-scale disruptions such as blackouts. Understanding the factors contributing to blackouts and the measures to prevent them is crucial for maintaining grid stability. A blackout is a widespread power outage that can affect a large geographical area and disrupt essential services. Blackouts can be caused by various factors, including equipment failures, natural disasters, and cyber attacks. Cascading failures, as seen in the 2003 blackout, occur when the failure of one component triggers a series of subsequent failures, leading to a widespread system collapse. The 2003 blackout originated from a seemingly minor event, a tree branch touching a power line. This event initiated a chain reaction that cascaded through the grid, causing widespread power outages. Factors contributing to grid vulnerability include aging infrastructure, increasing demand for electricity, and the integration of renewable energy sources. Aging infrastructure is more prone to failures, while increasing demand can strain the grid's capacity. The integration of renewable energy sources, such as solar and wind, can introduce variability and intermittency, making grid management more challenging. To prevent blackouts, several measures can be implemented, including infrastructure upgrades, enhanced monitoring and control systems, and improved coordination among grid operators. Infrastructure upgrades involve replacing aging equipment and building new transmission lines to enhance grid capacity and resilience. Enhanced monitoring and control systems provide real-time visibility into grid conditions, enabling operators to detect and respond to potential problems quickly. Improved coordination among grid operators ensures seamless communication and collaboration during emergencies. Moreover, investing in smart grid technologies can enhance grid resilience and enable more efficient power management. Smart grids incorporate advanced sensors, communication networks, and control systems to optimize grid operations and facilitate the integration of renewable energy sources. Load shedding is a controlled reduction of electricity demand to prevent overloading the grid during peak demand periods. Load shedding can be implemented manually or automatically based on predefined criteria. Black start capability refers to the ability of a power plant to restart without external power sources. Black start capability is essential for restoring power to the grid after a blackout. Islanding is a technique that allows a portion of the grid to operate independently from the main grid in the event of a disturbance. Islanding can help to isolate faults and prevent them from spreading to the rest of the grid. Risk assessment is a systematic process of identifying and evaluating potential threats to the grid. Risk assessments can help grid operators to prioritize investments and implement appropriate mitigation measures. Resilience planning involves developing strategies and procedures to prepare for and respond to blackouts and other grid disturbances. Resilience planning should consider a range of scenarios and involve all stakeholders, including grid operators, government agencies, and consumers. The North American Electric Reliability Corporation, also known as NERC, is a non-profit organization responsible for ensuring the reliability of the bulk power system in North America. NERC develops and enforces reliability standards, conducts risk assessments, and provides training and education to grid operators. The Federal Energy Regulatory Commission, also known as FERC, is a federal agency that regulates the transmission and sale of electricity and natural gas in interstate commerce. FARC approves reliability standards developed by NERC and oversees the enforcement of those standards. State regulatory commissions regulate the distribution of electricity within their respective states. State commissions also oversee the implementation of energy efficiency programs and renewable energy standards. Electricity consumers play an important role in grid reliability by conserving energy and participating in demand response programs. Demand response programs provide incentives for consumers to reduce their electricity consumption during peak demand periods. By understanding the factors contributing to blackouts and the measures to prevent them, we can work together to ensure a reliable and resilient power grid. This involves investing in infrastructure upgrades, enhancing monitoring and control systems, improving coordination among grid operators, and empowering consumers to participate in grid management. These are a few factors to consider when talking about maintaining the grid. The integration of renewable energy sources, while beneficial for the environment, presents challenges for grid stability. The intermittent nature of solar and wind power requires advanced forecasting and storage solutions to ensure a reliable power supply. Energy storage technologies, such as batteries and pumped hydro, can help to smooth out the variability of renewable energy sources and provide backup power during peak demand periods. Investing in research and development is crucial for developing innovative solutions to enhance grid reliability and resilience. This includes research into advanced materials, energy storage technologies, and smart grid applications. Workforce development is also essential for ensuring a skilled workforce to operate and maintain the power grid. This includes training programs for engineers, technicians, and operators. Public awareness campaigns can educate consumers about the importance of grid reliability and encourage them to participate in energy conservation and demand response programs. The 2003 blackout served as a valuable lesson for the power industry and policymakers. It highlighted the importance of investing in grid infrastructure, implementing robust reliability standards, and fostering collaboration among grid operators. By learning from past experiences and embracing innovation, we can build a more resilient and reliable power grid for the future. When discussing grid resilience, it's important to consider the impact of extreme weather events, such as hurricanes, floods, and heat waves. These events can cause widespread damage to grid infrastructure and lead to prolonged power outages. Implementing strategies to mitigate the impact of extreme weather events is crucial for maintaining grid resilience. This includes hardening grid infrastructure, developing emergency response plans, and improving communication with the public. The cybersecurity of the power grid is also a growing concern. Cyber attacks can disrupt grid operations and cause widespread power outages. Implementing robust cybersecurity measures is essential for protecting the grid from cyber threats. This includes implementing firewalls, intrusion detection systems, and employee training programs. The increasing reliance on digital technologies in the power grid also creates new vulnerabilities. Protecting critical infrastructure from cyber attacks is a top priority for grid operators and government agencies. International collaboration is essential for addressing global challenges related to grid reliability and resilience. Sharing best practices and coordinating research efforts can help to improve grid performance worldwide. The power grid is a complex and interconnected system that requires careful planning, operation, and maintenance. By working together, we can ensure a reliable and resilient power grid that meets the needs of our society. We also need to be aware of the economic impacts of power outages. Prolonged power outages can disrupt businesses, damage equipment, and lead to lost productivity. Investing in grid reliability is a wise investment that can save money in the long run. We need to consider the social impacts of power outages. Power outages can disrupt essential services, such as healthcare, transportation, and communication. They can also create hardship for vulnerable populations, such as the elderly and people with disabilities. Ensuring grid reliability is a social responsibility. We should strive to provide affordable and reliable electricity to all members of society. The power grid is a critical infrastructure that underpins our modern society. By understanding the challenges and opportunities facing the power grid, we can work together to build a more resilient and sustainable energy future. This includes promoting energy efficiency, developing renewable energy sources, and modernizing the grid. We also need to encourage innovation and entrepreneurship in the energy sector. New technologies and business models can help to transform the power grid and make it more resilient, efficient, and sustainable. The power grid is constantly evolving. We need to be prepared to adapt to new challenges and opportunities. By embracing innovation and collaboration, we can create a power grid that meets the needs of future generations.